notes, PowerPoints, lecture recordings, everything else goes into the exam 2 module now in Moodle. So if you ever want to double check something, double check what was written, you always have that as an option. Just remember that. So chapter 3, and I'm gonna tell you, I'm gonna apologize. I really thought that I changed this, but the very beginning of it, I changed the ending of this chapter, shortened it, but I didn't shorten the first 5 slides, so I did shorten them a little. I promise it's not a huge amount of difference, but you'll see there's fewer slides. I'm trying to cut down on the number of slides per chapter. I keep trying to I don't need this slide. I don't need this slide. This is just too much, All right. So first, this one's the same. So remember in the last chapter, we introduced these subatomic particles, protons, neutrons, and electrons. So we talked about where they are, what their charge is, how big they are, so that variation. So this chapter kind of moves away from protons and neutrons, which is really what we talked about. That's really what determines isotopes. That's what determines the mass. So just remember, protons and neutrons, their big function is that they give the atom mass. But we said electrons are 2,000 times smaller. They have mass, so they do have mass, but they don't really change the mass of an atom because they're so much smaller than protons and neutrons comparatively. But electrons do have a function. So remember in sort of what those electrons do. So electrons themselves are outside the nucleus. They're negatively charged. I said that they're in constant motion. So they don't just sit there. Protons and neutrons kind of sit in the nucleus in that dense little core. But electrons are in constant motion. They actually have a specific path. So a lot like the moon orbits the earth orbits the sun, they call the path that electrons follow orbitals. So if we look at hydrogen, so hydrogen is the smallest of all of the elements, right? Its atomic number is 1. It only has 1 proton and 1 neutron, 1 proton and 1 electron. So that 1 electron, it's not just randomly moving around outside of the nucleus. It actually has a specific path that it follows. It's negative, the electron's negatively charged. It is attracted to the positive proton that's in the nucleus, but because it's moving so fast, it can't go towards it, but it doesn't go away. So that kind of, a lot like a gravity kind of thing, kind of keeps it in that position. The electron wants to get as close as it can to the nucleus, and so it is going to fall into the lowest of the energy levels, the level that is closest to the nucleus. So the small atoms, very small elements, especially like hydrogen and helium, they're going to have their electrons very close to the nucleus. It's going to make it a really small atom. So hydrogen has its 1 little electron in this path. Well, helium, if you look and follow all the way across, you see hydrogen and helium look like they're on opposite sides, but in fact, they're only differ by 1 proton. So helium has 2 protons and 2 electrons. Those 2 electrons also fit in the first energy level, but that is as many as it can fit. So this is like the maximum. I always think of it as being it's so small that you really can't cram but 2 electrons in that space. So that means when we go to lithium, the next one, now we're going to have electrons that are going to not fit in the first, in that small little orbital. They're going to have to be a little bit further out. So things that you find. Some elements they found on the periodic table is they found that they were really stable all by themselves. And the ones they found were the noble gases, right? So like if you have a sample of helium, it doesn't form a compound. If you buy a can of helium to fill up your balloons, it is nothing but helium atoms. They don't form compounds. You don't find helium combining like hydrogen and oxygen combine and form water. You don't see helium doing that. Helium can exist as an individual stable atom. So can neon, okay? So neon, they put inside of glass tubes that they can make into shapes and everything, like those neon lights. So they have like a coating on the inside of the light. when they run electricity through, the neon glows, and that's how you end up with those neon lights, but it's still just neon atoms. They don't form any kind of combination with other atoms. They're very stable. So they found, well, why are these noble gases so stable? And then why do other atoms form compounds like water, like CH4, like CO2? Why do other atoms have to combine? They really found that it all depends on the number of their electrons and how they're arranged around the atom. The goal is to create an electron arrangement that is very stable. Say that one more time. That's what I just said. Like when I first started, I said these are very similar things. Those two slides, I just combined them into one and kind of like shortened some of the wording of it because it seemed like it was like stuff that I was like, I don't really care about that. I don't really talk about that, so it doesn't really matter. But the key thing to remember is these electrons are negatively charged. They're moving around the nucleus in this orbital path. The orbital that's closest to the nucleus really has a shorter path, and so it has less energy. A way to think of it is if you look at this, if I have this electron, so this is the electron like of the hydrogen atom, and then I have an electron from a larger atom that's further out, if both of these have to make their loops in the same span of time, so say 1 second, so the inside loop and the outside loop, they both have to do their path in 1 second, which one has to move faster? The outside one, because do you see the outside one would definitely have a longer path? So if the little red electron has to just make a loop in a second, it just goes one like this. But the outside one's going to have to go much faster in order to go that further distance in the same period of time. So that's why the one closest to the nucleus can have lower energy, it can move at a slower speed. The further out you get, the faster those electrons are going to move because the further their distance is to their orbital. And so the rule of thumb is electrons always fill the lowest energy levels first, because like anything else, wouldn't you rather have the lower energy? Like, doesn't that sound easier? You're not going to have to work as hard to make your little path. So the lower energy levels always get filled first. You can think of them looking almost like a little staircase. So that first energy level, I said it only holds 2. 2 is the maximum that fit in that first energy level. You can't fit any more than just 2. So hydrogen has 1 electron in that first energy level. Helium has 2, and that fills that energy level. That creates stability for helium, and it's why helium doesn't form compounds. That is a stable electron configuration. But now, notice the next step. The next step looks pretty big. Okay, so the next step, the next energy level, this second energy level, it can actually hold 8 electrons. So it's further out, which means it's a little bit bigger. So more electrons fit in those orbital paths. You can have up to 8. Now, when we get into third energy level, it can actually hold 18, okay? Because it's even further out, a bigger orbital path potential, so you can actually put even more. And when you get up to 4, it's all the way up, it's up into the 40s, okay? So it gets higher and higher because think like the further out you get, the bigger the path, the more electrons you could fit in this large space, whereas the first one's so small, you can only fit just 2. So they just continue to increase. So this one can hold a max of 18 electrons, and it begins to increase as it goes. But we really don't talk about the very, very large elements. Really, we talk about 1 through 20, and we'll cover 1 through 20 in just those first 3 energy levels. So I also took and kind of like crammed this all onto one slide because it helps you to see what the periodic table tells you. So in this one, here's elements 1 through 20. It's 2 slides. I just merged them. I had to shrink them a little bit, but I think it's actually more helpful to see it this way. So elements 1 through 20 are listed in order, all the way from helium all the way to calcium. And so you'll just kind of on your periodic table sort of follow along. So if you see hydrogen, so hydrogen we said only has one electron, right? Because this is, you know this because this is the atomic number. Right? In a neutral atom, the number of protons equals the number of electrons. So that if you look at the number above the symbol, that tells you the number of electrons. So notice that number goes from 1, 2, 3, 4, 5, all the way down to 20. So we're looking at them increasing by 1. The first energy level, notice hydrogen only has 1, helium has 2. Notice there's no more than 2 in any other atom because this one is just 2 electrons is their mass. The second energy level, so I told you the second energy level can hold up to 8. So see how lithium has 2 in the first, 1 in the second, then beryllium is 2 and 2. Going across, boron is 2 and 3. So as you go down, do you see that the number of electrons in the second energy level increases by 1 until we get all the way down to, which is neon, right? So see neon? So neon has the maximum number. Well, where's neon on the periodic table? It's the noble gas. So just like, remember I told you that helium fills the first energy level, it's a noble gas. It's stable. Neon fills the second energy level, it's a noble gas, and it's stable. So these have similar properties, and they also have full outer energy levels. So now, going along, once we fill the second, now we start filling the third. So notice starting with sodium, magnesium, aluminum, silicon. So notice sodium, the first energy level has 2, because that's full. Second energy level has 8, now it's full. The third energy level is now where you find the last one. So there's 1 in that outer energy level. You see as you go across, if you look on your periodic table, sodium, then magnesium, then you jump all the way over to aluminum, silicon, phosphorus, sulfur, chlorine. That's just going across the row on the periodic table, that third row. Notice that the numbers of electrons just increase by 1 in that third energy level until you get all the way over to number 8. Number 8 is, this is, what is AR? This is argon, and where's argon on the periodic table? It's a noble gas. So they started seeing this trend. Notice that all of these are in a column. All of these, all the ones that I've circled in purple or boxed off in purple, all of these are noble gases. All of these either have a full energy level or they have 8 as their outermost number of electrons. The outer energy level having 8, they found that created stability. So what do you think you would find with krypton? How many electrons in the outer energy level? 8. They saw the same thing. So going down, helium, neon, argon, krypton, xenon, all noble gases, all of them except for helium, have 8. And helium only has 2. Why? Why does helium only have 2 and it's stable? Because the first energy level only holds 2. So helium's kind of an exception to the 8, but if you remember, first energy level only holds 2. That's why helium is so stable. So I circled all of those ones. Okay, so now let's go back and I put them together like this because I want to go back. I want you to look at, if you look at hydrogen, lithium, sodium, and calcium, they all have what in their outer energy level? They all have 1, and where are they on the periodic table? They're all the group 1. They're all in the first column. So you don't actually have to memorize electron configurations. I don't want you to have to memorize the number of electrons in the first energy level. I don't care about that, okay? Instead, I just want you to be able to use the periodic table. So if you look at your periodic table, do you find helium, sodium, and potassium? See, they're all in the first column. See at the top, they have a 1A on your laminated page. Up there, it's a Roman numeral, but it's the number in front. So see the little Roman numeral, it's an IA. So Roman numeral I means 1. But on your periodic table, they don't even use the Roman numerals anymore. I kind of went to that because, see the number 1? That tells you how many electrons in their outer energy level. You don't have to memorize it, okay? So then, what do you think the second column? Look at beryllium, magnesium, and calcium. They all have 2. So do you see that they're all in group 2A? So the number in front of the capital A at the top of the column for the first 2 and all of the last 6 columns, they call those the main group, that Roman numeral, or not Roman numeral, but the number in front of the capital A tells you the number of electrons in the outermost energy level. Right? So this is 1A, this is 1A, this is 1A. So it doesn't matter which one we look at, so we could pick any one. Notice that nitrogen, this is group 5A. And then go down and look at phosphorus. This is group 5A. So you don't have to memorize which one's which. All you have to do is look at the periodic table, and that will tell you the number of electrons in the outermost energy level. So their importance, the energy levels that are underneath are full, right? So when you look at carbon, carbon has 2 electrons in the first energy level. You agree that's full? Okay, so that means that energy level is full and stable. It is the outer energy level that's not full. And they found that, what do you need in order to have stability? The outer energy level should have how many? 8, right? Because that's the noble gas characteristic. So noble gases don't react with things. They're extremely stable. But look at all the ones that don't have 8. Pretty much everything except the noble gases. So that means all other elements are reactive. So if you have any single atom that doesn't have 8, except for hydrogen and helium because they only need 2, but any other atom that exists as a single atom that doesn't have 8 electrons in its outer energy level, it's going to want to interact and form bonds, compounds with other atoms. So that's really like the reason that you end up with H2O. It's because hydrogen by itself is not stable. Oxygen by itself is not stable. But if they can combine, then they can create stability by achieving this 8. Okay, so the number of electrons in the outer energy level is really what dictates how they're going to react and what kind of bonds they're going to form, because they're the ones that aren't full. The ones that are in the inner layers, the inner energy levels, they're already full, so you don't really have to worry with them, and you really can just pick out how many valence electrons or how many outer energy level electrons an atom has. So the term valence is really just referring to the electron number in the outer energy level. And like I said, you can always figure this just by looking at the number in front of the capital A on the periodic table. So they use Lewis dots as a way to try to show or display the number of electrons, and that way you can then show like how they either are moving or how they're sharing, how bonding actually occurs. So when you do a Lewis dot structure, you always just put the symbol. So I'm going to use neon as the first example. You'll always put just the symbol, and then you will add a dot for each electron in the outer energy level. So you always just look at the top of the column. So whatever the number is in front of the A, that tells you how many dots you're going to put. So maximum would be 8 because that's the most stable. You will always have up to 2 dots above, 2 dots below, 2 dots to the left, 2 dots to the right. And so neon has 8. So that means that you will have 1, 2, 3, 4, 5, 6, 7, 8. So that just is showing or displaying the electrons in the outer energy level. It just doesn't show the ones on the inner energy levels because they're already stable. It's just the outer one. So just remember, it's these numbers. And they call these the main group elements. And so notice this is elements 1 through 20. We will also include bromine and iodine because those are also here, and we do talk about them. But pretty much, Those are the main group ones that you need to be concerned with. So here's a practice. You put the Lewis dot structure, look at your periodic table, and put the Lewis dot structure. Just fill in the dots for each of these. There's no right or wrong. There is no like, oh, you have to have them all on the left side, you have to have them all on the right. The goal is always have no more than 2 above, below, to the left or right. Okay? So you might put 2 on the left, 2 on the right. You might put 2 above or 2 below. If you have to put 2, wherever you want to put them, you just have to make sure, 1, you have the right number of electrons, and then 2, you never put more than 2 dots on a side. Okay? Okay, so you tell me, how many dots did you put for sodium? 1, okay? Doesn't matter if you put it there or you put it wherever, as long as there's 1 somewhere. Okay, don't get hung up on that part. What about magnesium below? 2. Right, so you're just looking at the group number. Aluminum is 3. Okay, so you could have aluminum like this, or you could spread it out and have 1, 1, and 1. Oxygen. Go ahead. Yep, doesn't matter. Okay, so she's saying if you had this, that'd be fine too. The kicker is don't have more electrons than what the number needs to be, and never put more than 2 dots on any side. So don't stick for aluminum, don't put all 3 dots on one side. Have 2 and 1, or you could have 3 singles. Doesn't matter, as long as you just don't have more than you need, and make sure you don't put more than 2 per side. So oxygen. 6. Now with oxygen, I will tell you with the nonmetals, so remember your nonmetals are the ones over here. With the nonmetals, trying to make sure that you put dots on all sides if you need them. So like with oxygen, and technically it would not be wrong if you put 2, 2, and 2, but left a side blank, but it makes it more cumbersome in doing bonding. So in this, if you have more than 4, spread them out, or really 4 or more, spread them out. So you see that oxygen has 6. So 2 sides should have 2, 2 sides should have 1, but it doesn't matter which sides those are. If you put them top and bottom 2 and the sides 1 each, that's fine. Both tops have 1, 2 sides have 2, that's fine. So it doesn't matter how they are, but do spread them out if you have 4 or more. So like with nitrogen, 5. So where did you put your double dots? At the top, but it's fine if you put them at the bottom. It's fine if you put them on one of the sides. The thing is to spread them out. So like this would not, look, now my pen's acting wonky. This would not be wrong. It's like spider webs. Okay. Argon. They have 8, right? So remember in this, that means I've got 8 dots. But no more than 2 per side. So don't stick like 4 on one side. Make sure that you spread them out like that. Chlorine is going to be 7. Does not matter where the empty one is. Just remember that there's 2, 2, 2, and one of them has to be a 1. Fluorine, 7. So this one, I could go like this. Just so long as there's a single somewhere. Pair, 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 and 1 single. Phosphorus, 5. And so in this, spread them out. Okay, so if you have 4 or more, spread the electrons out, put 1 electron on each side, and then start pairing them. So carbon, you're going to do 4 singles. 1, 2, 3, 4. It will just put you in easier mode when trying to do covalent bonding. Sulfur, 6. 1, 2, 3, 4, 5, 6. And then hydrogen. Wee little hydrogen has just 1. Okay, so remember, you don't have to memorize this. All you have to do is remember that's something off the periodic table. So if that's something that you're like, I've got to remember that I use the periodic table, put a note. Start your little note card now. Start your kind of like list of details that maybe I want to be sure I remember. So after each class, I suggest you kind of start that. And then when it comes time to do it, then you go back and look at those details maybe you were unsure of. Maybe now you remember that one. So you don't need to put it on a note card, okay? You want to try and put your details on the note card that you really think are going to help. All right, so what they found is this noble gas thing. Noble gases have 8 valence electrons except for hydrogen, right? So they found that is a stable electron configuration. So the term octet, because when you think of octet, you think of 8, right? Like an octopus or an octagon. So oct means 8. And so atoms that have 8 are going to be stable. Atoms that do not have 8 valence electrons are going to interact in order to form bonds to create a stable 8. So it's always the goal. You always want to think in your head, okay, I got to make 8 total. That is going to create this stability. So some atoms are going to give up their electrons. Some atoms are going to accept electrons. Some atoms are going to have to share electrons in order to create stability. But this is how we end up coming up with chemical bonds. So the whole reason you have compounds is all because of this drive to create this stability. So see, I made this one really big because it was way too small. It didn't really change too much in wording, but I tried to make the image a whole lot bigger because I used to have to blow it up and I was like, I can't even see it standing here. All right, so this one, the first example, this is ionic bonding, okay? So if you look at a nonmetal, so remember, you got to remember, nonmetals are to the right of the zigzag line. The metals are to the left. So again, you don't have to memorize which are metals, which are nonmetals. Just look for the zigzag line. And this laminated, it's not up there, but the laminated version has it darkened so that it's really clear. That staircase or zigzag line shows you where the differences are. So finding chlorine, you see that it's number 17 over on the left. See that chlorine has 17 protons and 17 electrons as an atom, right? So if you look at the element and you see its atomic number is 17, so that's how you know there's 17 protons and electrons. But 17 means that chlorine has how many electrons in its outermost energy level? What group is it in? 7, right? So looking at the periodic table, you know this, right? It's got 7. If it could get just one more, that would give it 8, and that would make it like a noble gas. So chlorine has a very strong attraction for any electrons that might come its way. So if the opportunity comes, chlorine is going to suck an electron away from another atom. And in doing so, look at what it does to its number of electrons. So now over here, we have chlorine. And if we say that this, we'll just use a different color. Here's an electron. So now chlorine's got this. So do you see now it's got 8 electrons around it? Its outer energy level is stable. But in doing this, now the numbers of protons and electrons are not the same. Here, it had 17 protons, 17 electrons. You see positive and negative protons and electrons balance. But now it has 17 protons and 18 electrons. So it has one more negative electron, which means its charge now is a -1. So they don't put a 1, kind of like H2O. You don't put a 1 after O. Same thing, if it's a -1, they just put a negative. It's fine if you want to start off and you want to like write that -1 so that you remember the negative means there's just 1, not 2 or 3 or 4. So now this is not considered an atom anymore. Now this is considered an ion. So an ion is really an atom with a charge. An ion is an atom with an unequal number of protons and electrons, and it only does this just to create stability. So chlorine gas, they had a spill about 4 years ago. There was a truck carrying chlorine gas down 95, and it got around Smithfield, Johnson County, got in an accident, went off the road, flipped over. They had to evacuate about a quarter of a mile all the way around where that accident was. There was a school that was less than a quarter of a mile away. Like they had to evacuate the school because chlorine gas is very toxic. If you inhale chlorine gas, it will react with the lining, the tissues in your lungs, and cause severe damage. So chlorine as an element is very reactive, and it's all because it has 7 electrons, and it just wants that one more. So it's going to try and get that one more electron wherever it can. whether it's your lung tissue, or if it's the air, or if it's water, anything it comes up against or comes up with, it would try to react with. Very typical of these elements. Okay, so let's look at what happens with sodium. So sodium's a metal, chlorine's a nonmetal. So sodium, when you look at its Lewis dot structure, what did we say it has? Na just has a 1, right? Because it's in group 1, so it just has a single dot. So sodium, if you look at its list, there's 2 electrons in the first energy level, there's 8 electrons in the second energy level, and there is that 1 electron in the third. So if you look at sodium, see its atomic number is 11. So it has 11 protons and 11 electrons. So that's how its 11 is arranged. So there's 2, 8, and then 1. So that's that little valence electrons, the 1 in the third energy level. If we could get rid of this, the next level in is what? 8, right? So the next, if we could get rid of that 1 electron in the outer energy level, the next level in is a noble gas. So this is why sodium is like trying to like throw its electron to anything that it could possibly come against, anything that might come near it, extremely reactive. So I told some of the classes, I'm not sure I told everybody, but sodium metal, if you have a pure sample of sodium metal, it actually has to be stored under kerosene. So kerosene is a lot like gasoline. So you have the sodium metal, it's stored in a container with kerosene on top because it will react with the air. You have to store it so that it can't. It'll react violently with water. If you take a piece of sodium metal and throw it in water, it reacts so violently with the water that it will cause the water to instantly boil. So it's like, it like bounces. It like literally generates so much heat. It like bounces and like you see all this flying smoke, everything else. As it boils that water, it's that reactive. But if it can get rid of that 1 electron, here's our 1 electron right here. Now it's a ion. So notice here, how many protons? Still has 11 because that's what defines sodium, right? It keeps the same number of protons, but it drops the number of electrons from 11 down to 10. So now the charge on the sodium is positive. So you can think of it as being Na. It's fine if you wanted to put a +1 or if you just put a plus. If you see just a plus, remember that means there's just a +1, a single positive charge. So now this is a sodium ion as well. So just remember, ion means that it's an unequal number of protons and electrons. Metals always become positively charged. Metals like sodium, potassium, calcium, magnesium, beryllium, aluminum, all the metals we're going to talk about, they always lose their electrons because they never have very many in the outer energy level. Sodium has 1, calcium only has 2, magnesium has 2, lithium only has 1. So the ones that only have just a couple of electrons, it's easier for them to get rid of their electrons than to try and pick up 7 or 6. That's really not going to happen. It's just easier to get rid of them and have the next level down become their outer energy level. So now we put them together. So I told you sodium metal, extremely reactive. Chlorine atoms, very reactive. But if we put these two together, the sodium immediately drops its electron. All right? So it immediately transfers its electron to the chlorine, which then leaves the sodium ion, Na with the plus, and the chloride ion, the Cl with the minus. So this one ends up negative, this one ends up positive. What do you know about charges? Opposites attract, just like a magnet. And so notice how now they like stick together. The sodium ions and the chloride ions stick together. That attraction of having this oppositely charged ion creates an attraction. Now I have not 2 atoms. That is a compound. Right? So remember in our pure substances, you can have elements. So like sodium by itself is an element, chlorine by itself is an element. But now that I have NaCl, now I have made a compound. 1 sodium and 1 chlorine have combined making a compound. And so what's its common name? Sodium chloride? It's table salt, right? You put this on your fries, right? So you start off with these two super reactive atoms, and they are so stable now that they're added, you have them in food. There are sodium and chloride ions floating through your blood right now. It's not sodium and chlorine atoms, it's sodium and chloride ions. Sodium is really important in water balancing in your blood. Anybody that's eaten super salty meals knows that, like, then afterwards you get like puffy hands, your rings get kind of tight, right? That happens to me after I have Chinese food, okay? Because of the MSG, which is monosodium glutamate, so it has the salt in it. So that creates that. Sodium is extremely important in trying to maintain that water balance, and chloride ions are really important in maintaining the charge balance with all of the other positive ions you find in the blood. That's the ionic compound. And just knowing this, like everybody knows, so NaCl, what do you call it? Salt, or its technical name is sodium chloride, right? So that tells you how you name all ionic compounds. So the first name of the element, it's always the metal. If you have an ionic compound, you always write the metal first. So you never see ClNa. Nobody ever says that, right? It's always NaCl, right? The metal is always written first in a formula, then the nonmetal. And when you say its name, what part of the first element do you use? If it's sodium, that's the whole name, right? You always use the whole name of the metal. But you don't for the second one. So how does that change? So we went from sodium and chlorine to sodium chloride. You use the first part of the nonmetal and you just add IDE. Is the first part of the nonmetal, but you're going to always add what? The ending is always going to be IDE. Ooh. Okay, so we've got some steps that we're going to do. Like I said, you list the first, you list the metal, then the nonmetal. Now, it's pretty convenient that I chose sodium chloride as the first one to do, because sodium chloride, the sodium becomes positively charged, the chlorine becomes negatively charged. Do you see that they're like a 1 in 1? So the sodium has a +1, chlorine has a -1. So they're already equal charged. But what about the second one? So let's look at magnesium and chlorine. Right? So if you have magnesium and chlorine, magnesium has how many valence electrons? 2. Good. Chlorine has 7. Right? So you know that neither of them are stable. Right? So in order for magnesium to become stable, what's its charge going to end up being? So just like we said, the sodium's going to lose its outer electron, magnesium's going to lose 2 outer electrons. So magnesium needs to lose its 2 valence electrons in order to be stable, so it'll end up Mg with a +2 charge. Once it loses its 2 outer valence electrons, the next level in is 8. Okay, so the metals are always going to lose their valence electrons, and that tells you what their charge will be, right? So their group number will be their charge. So magnesium's in group 2, so you know it ends up with a +2 charge. But now chlorine, what? Yes, because that would be even less stable, right? So if they only lost 1, then that would make them like sodium. Like that would make them even more reactive. They've got to lose all those valence electrons. Yes. So they're group, and you don't even have to like do the valence electron dots. You can just look at the group number at the top. So their group number is going to tell you what their charge will be. Okay? So now chlorine though. So what did we say with chlorine? What happened? It ends up gaining. And how many does it gain? 1. So chlorine's in group 7. So if it becomes a -1, one way that you can determine its charge is if you take 8 minus its group number. So if I take 8 minus 7, which is in group 7A, that is going to tell me its negative charge value. Because it's always going to gain an electron. It's going to gain electrons until it makes 8. So this is going to be Cl with a negative charge. So now do you notice that these two are not exactly the same? So you notice that magnesium has a +2 charge, chlorine has a negative charge. So where sodium and chlorine were 1 and 1, these ones do not have the same charge value. So I can't just say those make a compound because they would not be chemically neutral. Magnesium has a +1, so the chlorine has to have a -2. I can't make a -2, but I can use 2 chlorines. So a really simple way of being able to figure this out is you do this. Assign the charges for the individual atoms for the metal and the nonmetal, then take the charge, swap the charges to determine the formula. So you're going to just take the charge on the magnesium tells you how many chlorines. The charge on the chlorines, this would be a 1, remember, would tell you how many magnesiums. So you just take them and you swap them. And that tells you the formula. Oh. It's not. Right, because now it's neutral. So do you see that now this is a +2? That magnesium's still a +2 ion. Each chlorine is a -1. And how many do I have? From the formula? I have 2 of them. Okay, so in this, remember the magnesium's a +2, the chlorine's a -1. This 2 tells me how many chlorines. This 1 tells me how many magnesiums. So you take the charges and swap them. The charge for the metal tells you how many nonmetals. The charge on the nonmetal tells you how many metals.
So you don't have to write it down when you do the formula.
No, I mean, I find it's easy if you you list the metal and the nonmetal, assign the charges, swap them, and then just write the formula as a final number.
So you just multiply, like,
Okay, let's try another one. All right, so let's do potassium and oxygen. So you tell me, look at the periodic table. Potassium, what's its charge going to be? It's a +1, right? So potassium's in group 1, so it's a +1. What's the charge on the oxygen going to be? It's got 6, so 8 minus 6 tells you it's a -2, right? So remember that you're going to take 8 minus 6a, tells you it's a -2. So that's how you determine the charge. So now I'm going to swap. What's the formula? So the charge on the oxygen tells me how many potassium. The charge on the potassium tells me how many oxygen.
so the pluses and the minuses kind of go away after you swap them.
Right. Well, the pluses and the minuses are still there, but when I write a formula, like when you say NaCl, do you put pluses and minuses in the formula? No. Right? You're just listing just the elements according to the number of each. So always remember the number after the symbol tells you how many of that symbol there is. So let's try one more. So do Ca and N. So what's calcium's charge? Look on your periodic table, +2. Right? Remember the metal, it's just the group number, tells you the positive charge. Now, nitrogen. I'm going to move this one over, K2O. So it has 5. So what's its charge? -3. Good, right? Because remember, for the nonmetal, it's 8 minus the group number. And it's always a negative number. The metal's always a positive number. The nonmetal's always a negative number. So this is going to be 8 minus its group, which is 5A. So that tells me that this nitrogen is a -3. So that's how you assign the charge for the nonmetal. Now swap. What's the formula? Does anybody not see how you get that? You do it exactly the same every time, okay? So remember, there's some things like I tell you, like, just do it exactly the same every single time. This is one to practice, but you're going to set it up the same. So list your metal and your nonmetal. Then assign the charge to the metal. That's always the group number, and it's always positive. Then assign your charge for the non-metal, which is always 8 minus its group number. Then just swap those charges. Now, if you look at calcium and oxygen, this one here, when you assign the charges for these, calcium is in group 2, it's a +2. Oxygen's in group 6, so 8 minus 6 makes -2. But notice if I swap these, they're both 2s. So the rule with that is to simplify. So the simplest whole number ratio that calcium and oxygen would exist in is a 1-to-1. So I always kind of look at this and say, oh, well, they're already equal. The +2 and the -2 equal each other, so they exist in a 1-to-1 ratio. So just remember, if you came up and they were both, it's either going to be like you might have 2 and 2 or 3 and 3. That's the only time you're ever going to see this. But you could potentially see a metal with a +3, a non-metal with a -3. They would exist in a 1-to-1 ratio. So now the last one, the fun part. So you tell me the names of all the ones we just did. So tell me the name of K2O. All right, so K2O, what do you think that one is? Potassium oxide, right. All right, so potassium oxide. What about Ca3N2? Calcium nitride. First part of the nonmetal plus IDE. So let's look at the nonmetals. So if we have nitrogen, it becomes nitride. If you have oxygen, it becomes oxide. Good. If you have fluorine, it would become fluoride. Everybody knows that because of toothpaste, right? Okay. If you had phosphorus, it becomes phosphide. It's the first part of the word, kind of like phospha, and then IDE. What about sulfur? Sulfide, chlorine. And then bromine. And then iodine. Iodide. Yeah. Okay. Yeah. So that one's just another strange one because it seems like there's a lot of I's in that word, but that's actually right. Okay. So that one would be, this would be calcium, whole name of the metal, first part of the non-metal, and add IDE. Okay. Nope, it came. But see, now it won't let me change pen color. I can write, but I cannot change pen color. This is when I want to throw my pen when I'm teaching, because, so here they come again. So look. Huh? I change pen color all the time. Oh, I come down here to the little menu icons that are now gone and won't come back unless if I close my PowerPoint and bring it back up, it comes back.
So is that application part of PowerPoint or is that something else?
Yeah, this is PowerPoint. It won't. Now I can go like this, and I can go to pointer options and ink color and change my ink, but it will not let me see the little like, it's like a little menu tab that shows up on the bottom that it won't show up again.
Disconnected PowerPoint switch to like keyboard mouse mode.
They haven't detected the pen back yet.
Right. So you're probably gonna have to, like you said, exit for it to see that you have the pen.
So there's, but see, it's in pen.
So PowerPoint the application isn't recognizing the pen.
So is there any way that I can change any of those to make it do that? Because see, that's what I thought, well, maybe
Is
in,
it presentation view? Does it show presentation view? Does it show back up?
no, now I'm back. And I come back here, and then I duplicate it just for being able to write it. But nope, it's still not there. But now if I do this, if I use my finger, pull my pen away and use my finger, I can like change. But if I come back, oh, it just came back. Hold on. Yep, now it's back. I didn't shut it. One last thing. We're just going to introduce it. We're not going to cover. Got to catch up there, buddy. Again. Thank you. Fingers crossed, maybe. Maybe they'll all go off and figure it out. I have a lot of respect for them because, like, personally, I'm just done. All right. So there's two, like, I call them like weird ionic characteristics. One of them is when we're not talking about the main group. So if you look on your periodic table, You see this group, there's 10 columns in this middle area. Notice they don't have a capital A at the top, they have a B, right? Do you see all the groups with the B? They call those transition metals. Transition metals are kind of strange because they don't always lose the same number of electrons. The only ones that we're going to worry with are the ones that you might actually see again. So here are the three: iron, chromium, and copper. Iron, chromium, and copper can lose more than a specific number of electrons and create stability. So iron can either lose 2 electrons and become a +2, or it can lose 3 electrons and become a +3. Chromium's the same way. So remember, chromium's number 24, iron's 26, and then we go across, copper is number 29. Chromium can also lose either 2 electrons or 3 electrons. Copper can lose either 1 or 2. So those are the only 3. And in fact, if you look at your this is kind of like your summary of all of the possible ions. So this is a good one to look at. I will tell you, I'm not going to ask you any of those. Rubidium, strontium, cesium, and barium. You didn't have to learn those names and symbols. There's chromium, iron, and copper. You don't have to worry about having to do ionic compounds with any of these other ones. So there's a lot of them, but we're just going to really focus on those 3. So for example, if you have iron chloride, okay? So when you look, iron can have a +2 or a +3 charge. So when you go to make a formula, you need to know which one it is. Is it iron 2 or is it iron +3? Which one is it? Because they're going to make different formulas. So starting off, what if I have iron with a +2? What would the formula be for that? It'd be FeCl2. So notice this is B. So if I had iron with the +2, chlorine's always going to have a -1 because it's in group 7, right? So when I do the swap here, I would have FeCl2. But what if I had this? What if I had Fe with the +3 in chlorine? What would the formula would be? FeCl3 if I did the swap. So do you see I could have 2 possible combinations of iron with chlorine? So how do you know? This is where you have to use what they call a Roman numeral. So the Roman numeral goes in between the iron and the chlorine. You use a Roman numeral 2 if it's iron with a +2 charge. You use a Roman numeral 3 if it's an iron with a +3 charge. So the Roman numeral tells you the charge on the metal. It doesn't tell you how many of the metal, because that's a common mistake. Doesn't tell you how many. Put a note, the Roman numeral tells you the charge on the metal. So when I go to name this one, I would call this iron 2 chloride. I would still name whole name of the metal, first part of the nonmetal plus IDE. That part's the same, but with iron, copper, and chromium, you have to have that Roman numeral in between to show the charge. So I'd call this iron 2, and I don't care if you use parentheses. I think your book really wants you to. I don't. If you just had a 2, if you just had the Roman numeral 2, that's fine. But this would be iron 2 chloride. See if I can write really, really small. Whereas the FeCl3, this would be iron 3 chloride. Okay, so what if I had, what time is it? Oh, I still have a few minutes. So what if I had chromium 2 phosphide? So if you're given this name, write the formula. Chromium 2 phosphide. You would never see that. Iron, it'd be the same thing as saying like calcium only loses 1 electron. It's going to lose 2. Okay? So iron is only going to exist stably as a +2 or a +3. Well, that's not really true, but we're just going to say that. for our class. There are some instances of +4s, but that's pretty rare. Okay, so for us, these are the only ones. These are the only these three. These are ones that you need to know their names and symbols anyways. One of the reasons I gave you those in chapter 1. So chromium, iron, and copper. You should know the names and the symbols for those back from chapter 1. Those are the only three that you need to worry with that are going to have more than one possible positive charge. So if it's chromium 2 phosphide, what does that tell you? Cr is a +2. That Roman numeral 2 tells me that chromium's a +2. And then phosphide is a -3, or 3 negative. -3, 3 negative, exactly the same, that's fine. You can write it 2 plus or +2, that's still the same. So when I do the swap, what's this formula? Yep. Okay, assign the charges and swap. What if I had blah? What if I had this? Cu3N. What's the name? It's copper nitride, but because it's copper, I can't just say copper nitride. It's not copper 3, right? The Roman numeral does not tell you the number of coppers. What do you have to do? Swap them back. You can think of it as the reverse swap. What's the charge on the nitrogen? Nitrogen's a -3. Do you see the -3 and the 3 for the copper? So what does that tell you the charge on the copper is? It's a +1. So do you see in this, I took the subscripts and swapped them in reverse. So the number of each atom tells you the charge on their opposite atoms. So the number 3 and this -3, I know the charge on the nitrogen, right? Because nitrogen's in group 5, 8 minus 5 tells you the nitrogen's a -3. But see how those match? So the nitrogen's a 1, so that tells me the copper has to be a +1. So it's like a reverse swap to figure that out. So this would be a copper 1 nitride. Yes. And I don't care if you use the parentheses, but you definitely have to have a Roman numeral. So note for yourself, iron, copper, chromium, they will always have a Roman numeral in their name. Iron, copper, and chromium. Those are the only three. So you may need to do a couple of examples for yourself. How do I name it? How do I write the formula? And I will tell you that copper 3 nitride is like the most common mistake that I see with these, is people see Cu3 and go, oh, it's copper 3. Well, copper 3 doesn't exist. Copper only exists as a +1 or a +2. So that's mistake number 1. But then also, it's not telling you the number of copper. It's telling you the Roman numerals is you got to determine the charge. Right there, the 3 that I circled, chromium, iron, and copper. Those are the only 3. See those 3 that I've got in purple boxes? Those are the only 3 transition metals that you have to worry about that have the potential of more than one charge. So you have to use a Roman numeral with those. All right, I'm going to stop there. Notice, though, I have a couple of practice questions with these. So on Tuesday, we will start off, we'll do some of these, and then we got to talk about polyatomic ions, which is the last weird ionic kind of group. And from there, we can then go on to covalent.